Welcome to this presentation on real-time control of a monolithic piezoelectric nano-positioning system. My name is Solomon Vula. The objective of this project is to design real-time control algorithms for a cruciform monolithic piezoelectric nano-actuator system to improve transient response and minimize steady-state error. You can see a picture of the system on the right of the slide. Before we proceed, we need to realize that at the heart of the piezoelectric positioning technology is a piezo ceramic actuator. It has a crystalline structure which expands slightly when an electric potential is applied and is known as the inverse piezoelectric effect. This property is exploited by nano-positioning technology. By changing the voltage applied and thereby very precisely control motion can be performed. In this project, we have designed two control algorithms. One was a LQR control plus observer with integral action, and the other was a PID controller using set point on eye technique. Later in the slides, we will see the results obtained while using a PID-based system and an observer-based system. We will be talking about the main differences between them and why we prefer one over the other. It should be noted that systems that work on paper do not necessarily work in the field. There's an ever-present act of tweaking and fine-tuning systems that is done even if the system seems perfect on paper. At the end of a performance evaluation was performed on both algorithms with certain testing criteria set forward for steady-state error, percentage steady-state error, RMS error, and finally percentage overshoot. As in any case, the final objective was to reduce the overshoot and the error as much as possible. Ideally, we prefer a zero value for both the previously mentioned parameters, but in reality, obtaining a zero value could be very difficult. In those cases, we satisfy ourselves with a value that is as close as possible to zero. In this slide, we see the differential equations that were provided to us for the system. Building the differential equations requires a thorough understanding of the system and how it behaves. Please note that all nonlinear equations needed to be linearized before proceeding with designing the controllers. This is because we cannot use any linear control theory on a non-linearized system. The zeta you see in the bottom of the slide has a very important role to play in the entire system. It is a damping ratio and characterizes the frequency response of a second-order ordinary differential equation. And damping ratio is a dimensionless ratio, it being the ratio of two coefficients of identical units. The damping ratio is a system parameter that can vary from undamped, where the value of zeta equals 0, to underdamped, where the value of zeta is less than 1, through critically damped, where the value of zeta equals 1, to overdamped, where the value of zeta is greater than 1. Now let us talk about the controller. But before that, we have another very important item that we need to discuss, and that is the zero-order hold. The zero-order hold is a mathematical model of the practical signal reconstruction done by a conventional digital to analog converter. The zero-order hold describes the effect of converting a discrete time signal to a continuous time signal by holding each sample value for one sample interval. Now, back to talking about the controller. A controller is the most vital component of any control system. It is responsible for the performance of the control system. It is a device or an algorithm that works to maintain the value of the control variable at a set point. A question that can be asked now is, why bother converting the signal to discrete from a continuous signal? This is because we are using real-time discrete controllers. On the bottom of the slide, we see the system's matrices obtained from the nonlinear segment. This involved linear algebra techniques to obtain. In this slide, we see the system matrices with the given constant values that we made for this system. Note that now it is this linearized discrete time model that will be used for our controller design. It should also be noted that there is a lot of other effort that goes into designing a normal system in the field in the form of using software like MATLAB or any other software. Not all systems can be derived and designed using pencil and paper. Patrick will be talking next about the first controller that we use to gain the desired output.
So our first controller is an LQR plus observer control with an integral action on the input side. The beauty of the industrial regulator is that we don't need to figure out what the optimal gain is for the state feedback K. We could just use Q and R to find the optimal value for K. Q and R are the state weighting and input weighting matrices respectively. If we want to put more emphasis on a certain state value, we can just adjust the Q value for the state, and K will adjust accordingly. The problem is that the LQR control requires full state feedback, or every state to be fully measurable. Just like a real-world system, we only have the input and the output of a system, or what we call a white box. We call it a white box because we know some of the insides of the box, as opposed to, a black box. In order to get the state values, we can use an estimation of those values, and over time, those estimated values will approach the actual true values. This is what we call an observer. So the observer plus the LQR is our full controller, but there's still an issue. The steady state error of this system is varying and not a constant offset. In order to account for the offset, we need to add an integral action before these two steps. This fully combined will make up our controller 1. Okay, on this slide, you can see what I was discussing in the previous slide. We have in the top diagram one is just the observer estimating the state values x hat, and that goes into the negative K, which is the LQR control optimal gain. Below this, we have a state feedback being fed into the summer with Ki, which is the integral action gain. You can see that the summer for the integral action is feeding the error of our command signal Y reference, which is our command signal, minus our output Y, which is the output of the plan. This diagram shows how we can account for that steady state variation. Okay, on this slide is the full Simulink diagram. So now we're building what we've just discussed in the previous slides. We could see at the start that we create our reference command, which is just a staircase function. Into the first summing junction, you can see that we are creating an error to be fed into the integral action. You can see the output of the plant Y is being subtracted from the command signal. Then below the plant, we have the state space representation of our observer. Notice that the observer also needs to not only know the output of the plant, but also the input to the plant. Without these two, you can't create a true observer. The output of the observer gets fed into the K gain vector, and the summing junction combines the integral action with the observer and the LQR to give our plant the control effort that it needs. The slide here shows the scope output that was in the Simulink diagram. Here we're looking at the command signal, the staircase, and then also the output of the plant. We're trying to get as close as possible to the yellow command signal. Yellow is the command signal that we're trying to follow, but with no overshoot and good response. You can see that the blue line, which is the output of our plant, performs very well in the tracking of our commands. Just a few comments in this slide to discuss the integral action. When we first created this control algorithm, we were getting a varying offset that we couldn't be fixed with a DC bias. Anytime we tried to offset it by a constant value, it would only account for one of those offsets. So it could be very, difficult to offset that steady state error. Just like the integral action in a PID controller, the integral will integrate the error over time, and that can bring us back towards the commanded set point. Okay, on this slide we're discussing some of the issues with this design. First and foremost, this took a lot longer to set up than the standard PID tuning and control. It also might have been a waste of time considering how the system performed with the PID control. The majority of control systems that I've worked on in my work has almost always been PID control because usually that's good enough. It also requires not only the use of software like MATLAB and Simulink, but it also requires creating a great model of your system, which can be difficult in the real world. Finally, on this side, we see a breakdown of the actual performance metrics of our slide. On the first row, you could see we're trying to track the actual staircase function, which is, we want to get as close as possible to that. The second row, you can see we have the steady state error, so we want that to be minimized as possible. And the same thing goes for the third and fourth row. The criteria for this didn't really account for rise time, but most importantly, in the requirements document, we wanted to have no overshoot. And you can see from here that there's a very little overshoot. There's also very little RMS error, which is good.
Hello, my name is Peter Malakawi. A brief introduction of myself. I graduated as electrical engineer in May 2019. I'm currently pursuing my master's degree in intelligent system online from NJIT. I should be graduating on May 2020, and my current role is control engineer. So today's presentation, we're going to talk about I'm going to represent you of the controller 2, the PID controller. So the PID controller stands for the proportional integral derivative controller, which is basically a control loop mechanism employing a feedback. It's widely used in industrial control system, and it continuously calculates an error of the ET, which is the difference between the desired set point and the measured process variable, and applies a correction based on proportional, integral, and derivative terms. The reference command signal change frequently, so that's why we separated the PID controller. The down plaque is only a proportional derivative controller, and the above one is the only integral controller with the zero proportional and derivative terms. The reason that we did that is the integral action always act on the error, but the derivative action always acts on the process variable or the output of the system itself. The beauty of this control algorithm is that the control effort is smoother using this method, and also there's a lot less calculations used here, not like the model-based algorithm on the previous controller. This method does not require a lot of calculations, and also but also on the other sides, it requires a lot of tuning and tweaking to achieve the required result. The next slide we have is the very good slide that actually explained the PID controller in animation wise. It give you the intuition of the proportional gain, the gain constant, the integral constant, and the derivative constant. So as you can see, the more gain constant you do, the more oscillation, and the more integral constants, the more you can offset the entire system up to the set point, and the derivative term will anticipate the change, and remove any oscillation of the system, as you can see. And the next slide, we're going to go through the block diagram in the Simulink. So as you can see at the beginning, there is a command signal staircase, and then we have a gain with the integral action. Down here, the BD proportional derivative controller, and we got the zero hold, which is responsible for discretize the entire system. As you can see, we fed up the process variable to the proportional derivative, and we fed the error to the gain and then the integral action. We're gonna explain later why we choose 25 as our gain value, and we put, as I mentioned earlier, we put the integral action here because we tried to the entire block BID block to fit with the error, but we didn't achieve the required results, so we choose to separate it. And since the integral action only act on the error, we fed it with the error, and the derivative acts only on the process variable. We fed it with the output of the system. The next slide is the actual simulation with the results, and as you can see, the system output match perfectly. Sorry for that. Match perfectly. We didn't get any oscillation, no overshoot, and it basically like the illustrated animation earlier. No overshoot, no oscillation, and a quick response. So on the next slide, we have some comments on the previous slides and the design of the controller too. As we mentioned earlier, we separated the BID block into two different ones, the integral action and the proportional and derivative action. And the reason we choose 25, we felt that this is the pre-amplification for the error signal, and from tweaking this gain value, we find it was the best trade-off for the oscillation and rising time. And as we mentioned earlier, the BID block at the bottom is fed with the output of the system, the process variable, and the BID block at the upper is the integral action and fit with the error only. The next slide. The issues with the design, the advantage of the system is that it doesn't require a mathematical model. No mathematical approach is required, no calculations, no complex calculation, but on the other side it requires a lot of tweaking and tuning, and since it requires a lot of tuning and tweaking, it also requires a lot of testing. And on the other hand, you have to have some intuition on what each gain were responsible for, like what's the gain term will do to the system, what's the proportional, what's the derivative and the integral terms will do also to the system. And it's not ideal compared to the model-based algorithm that we used in the first controller. I'm going to leave you with Mohammed to talk about the performance evaluation. Thanks.
Hello everyone, and thank you Solomon, Patrick and Peter for covering introduction, system model and real-time controllers block diagram. My name is Mohammad Rahman and I am going to cover to evaluate the performance of our two controllers we designed, and then I compared the performance in terms of 4 different performance parameters which were designed into 4 time intervals. First of all, we'll go through quickly the performance parameters that we use to measure our plant output. Here the system is evaluated on how well it can track the reference input signal, which is called Y reference, and what percent of overshoot we can tolerate and what is our steady state error. To do so, first important parameter is steady state value. It is the final value that the output of a plant is, and objective to keep the value as close to the Y reference signal. Second important parameter is steady state error, which should be close to 0. And the next parameter is the RMS error that measure how well the signal track the reference signal. And the last parameter is the percent of overshoot, that the output of the plant in reference to the input signal. We want as little overshoot as possible. In this slide, we are going to the performance evaluation of our two controllers. We have two simulation results here in this slide. The left simulation result is for the model based LQR with observer, and the right simulation result is for the PID, where we used set point on I. We separated integral part from the PD part to get the most optimum result. Both the simulation actually gave us almost similar result with very low steady state error and absolutely no or very small overshoot. That was our actual or ultimate objective to achieve. The reason we got less steady state error and less overshoot is the use of low sampling time. In our case, we used sampling time as 0.0001 second. Also, we used higher value of Q and lower value of R to achieve such fast and steady state performance, especially in our LQR based controller design. One important thing we need to show here from these two simulations result, which is pointed here with the red arrows. On the left simulation, we can see that the plant output changes the state 0 to 1, 1 to 2 and 2 to 1 and again 1 to 0 using time intervals, and the rise time and the set time to steady state is equal for all the 4 time intervals. Whereas on the right simulation, we have different rise and set time for wall time intervals that clearly tells the performance difference between LQR and PID controllers. Now we like to compare the performance between these two controllers we designed. To compare the performance, we used 4 time intervals as we discussed, as we told before, to measure 4 performance parameters. In the left table, the value represents the LQR based plant, and the right table, the value represents for PID based plant. Looking into the table and also in the simulation, we have shown in our previous slide, and also it is clear that controller 1 steady state value is very close to the reference signal value. For time interval 5 to 15 millisecond, reference signal steady state value is 1 and the controller output is also 1. For time interval from 15 to 25 millisecond, reference signal steady state value is 2 and the controller 1 output is also exactly 2. For time interval 15 to 35 millisecond, again output is 1, which is same as input. Looking into the steady state error, we have very less error as both the controllers at every time intervals, but controller 1 has less error than controller 2. Similarly, in terms of percent of overshoot, controller 1 has less overshoot than the controller 2 at first 2 time intervals and 0 overshoot at third and fourth intervals for both the design. So in the conclusion, we like to briefly summarize the advantage and disadvantage of two different controller we design. In terms of robustness and efficiency, model-based controller, in our case, which is controller 1, we designed using LQR-based observer, is more robust and faster than typical PID controllers, which is controller 2 in our case. In terms of cost and time, model-based controller design is costly and require more time to establish, but it is reliable and work on control algorithm and sets up and it sets up a lot of mathematical equations. On the other hand, PID controller can be used for most typical situations to solve immediate purpose that requires less focus and less money. In terms of performance objective, to meet a very specific performance, it could almost be impossible to implement than using PID algorithm. PID is more or like a trial and error approach, and sometimes certain gains do work and sometimes don't. That's all about our project. It was a great experience working together and playing with MATLAB to establish different algorithms and finally compare the performance of two different algorithms. Thank you.